We are now going to look at the MIPS pipeline data path and how to deal with what are known as structural hazards. A hazard is nothing but a condition or a situation in which the pipeline is not able to operate normally. That is, units of work don't move through the different stages of the pipeline smoothly. When this happens, this is called a hazard. There are three broad kinds of hazards in pipelines. The first is structural hazard, the second is data hazard, and the third is control hazard. Of these three, structural hazards are the easiest to deal with, data hazards a little bit more difficult, and control hazards are the most difficult to deal with. We will also discuss them in this order. This video itself covers only structural hazards. A structural hazard is nothing but a situation where there is a hardware limitation. Ideally, the different stages of the pipeline should be able to operate parallelly on different units of work. That is, ideally there is no hardware limitation. For example, in the bicycle pipelining case, we should have separate spanners for the third stage of fit wheels and the fourth stage of fit accessories. If this does not happen, it's called a structural hazard. In the MIPS pipeline, stage 1 involves access of instruction memory, and stage 4, which is the memory stage, involves access of data memory, which means that these two stages must be able to operate in parallel. That is, the instruction memory and data memory must be separate. Likewise, we must have separate adders for addition of PC with 4 and also for branch target computation. This is because the ALU is used for something else in stage 3. It cannot be used for PC plus 4 addition in stage 1. If it were used in such a fashion, that would be a structural hazard. One thing we must be clear on is that if there is a structural hazard, it doesn't mean that pipelining cannot happen at all. We can still use pipelining as much as possible, but there will be some delays. Let us understand this by using an example. Let us say that we have the same memory unit for instruction and data access. In that case, let's see how we can use the MIPS pipeline still by introducing additional delays. In this pipeline timing diagram, where time is flowing from left to right and different units of work are shown from top to bottom, we have 4 load word instructions one after another. We see that everything is fine until the third cycle. When we come to the fourth cycle, this first instruction load word wants to use the memory unit for data access, whereas the fourth instruction wants to use the same unit for instruction fetching. This is a structural hazard situation. We are going to resolve this situation by introducing a stall in the pipeline. That is, this instruction, the fourth instruction, is going to wait until this hardware unit, the memory hardware unit, becomes free and then only enter the pipeline by entering first stage. So if we do this, we see that one cycle is wasted due to this stall. This is also known as a bubble in the pipeline. Because of this bubble, we will see that this bubble in the pipeline is going to show up as a bubble at the end of the pipeline as well, which essentially means that we normally have one instruction finishing execution every cycle, but we notice that in this cycle, there is no instruction which is finishing execution. So this is a bubble which has shown up at the end of the pipeline as well. So in summary, structural hazards, the way to deal with it is to detect when they happen and stall the pipeline. Simple solution, but it has an effect in terms of instruction throughput. Let us now see how we can quantify the performance effect of these kind of stalls and how we can quantify performance of a pipeline implementation in general. Here is a question to start with. What is the CPI of a pipelined MIPS implementation going to be? The CPI in an ideal pipeline is going to be 1. This corresponds to the fact that one instruction completes execution in an ideal pipeline every cycle. So here we have modified the definition of CPI slightly by saying that it is the number of cycles taken on average per instruction completion. That is, we look at the end of the pipeline and see the rate at which instructions come out of that pipeline after execution. Now, if we have a pipeline with stalls, we are going to have this effect show up in the form of increase in CPI. Now, the CPI is going to be 1 plus fraction of stalls. So, the fraction of instructions which undergo a stall, that's the fraction of bubbles which will appear out of the pipeline. So, the CPI will effectively be 1 plus fraction of stalls. With this model, we can now evaluate the performance of a pipeline implementation. Let us take this example where we are comparing the performance of a multi-cycle implementation with a pipeline implementation of the MIPS instruction subset. Let's say that the multi-cycle implementation has a cycle time of 9 nanoseconds. Due to its various overheads, let us say the pipeline implementation has a slightly longer cycle time of 10 nanoseconds. Let us say the instruction mix is 65% register instructions, 15% branch equal, load word 15% and store word 5%. What is going to be the ideal speed up, assuming a pipeline implementation which has no structural hazards, and what is going to be the speed up when we have structural hazard in memory? That is, we use the same memory unit for instruction as well as data. In that case, what is going to be the speed up? Well, first we need to calculate the CPI in the multi-cycle implementation. Note that in the multi-cycle implementation, register instructions take 4 cycles to complete, BEQ takes 3, load word takes 5 and store word takes 4. If we compute a weighted average with these percentages, we will find that the CPI in the case of multi-cycle will be 4. Of course, in the ideal pipeline, CPI will be 1. So in this case, the speed up will be nothing but 4 times 9 divided by 10. This will be 3.6. In the case where we have a structural hazard, this is going to be modified as follows. The numerator will remain the same. The denominator will change corresponding to the fact that with structural hazard, the CPI is going to be 1 plus fraction of memory instructions, which is 0.2. So the CPI is going to be 1.2 times 10 nanoseconds. This will be 3. If you notice the MIPS pipeline stages carefully, you will find that there is yet another structural hazard potentially. We read the register file in stage 2 of the pipeline and we write the register file in stage 5 of the pipeline. So this is a potential structural hazard. Of course, we could resolve this situation by stalling. This would be a correct solution, but this is too expensive in terms of performance. This is because a large fraction of instructions are going to write the register file, and each such instruction, if we were to use a stall, will introduce a bubble in the pipeline, and this will be expensive in terms of performance reduction. So the solution which is used here is we write the register file on the rising edge of the clock in the first half of the clock, and we are going to read the register file on the falling edge of the clock. So the same unit is going to be used in different ways in the first half of the cycle and the second half of the cycle respectively. Now the order in which these two things are done, writing in the first half of the cycle and reading in the second half, is not arbitrary. It has a specific reason why it is done in this order, and it has to do with handling of data hazards, which we will look at when we come to data hazards. We have looked at many examples of pipelining of MIPS instructions without really looking at how this pipelining is going to be implemented. Let us start looking at that. To talk about the pipeline implementation, we need to talk about the data path and then the control. And just as we did when we went from the single cycle implementation to the multi-cycle implementation, we are going to talk in terms of modifications to the multi-cycle implementation. And we are going to see a pattern which was encountered when we went from the single cycle implementation to the multi-cycle implementation. The pattern being the modifications to the data path are simple, but the control is going to become much more complicated. The modifications to the data path from the multi-cycle implementation are going to be simple enough that I can describe them in this slide. So this diagram depicts the modified data path. We start with the PC, use it to read instruction memory. So in this particular implementation, I have assumed different instruction memory and different data memory to avoid the structural hazard we just talked about. Likewise, we use an adder specific for stage 1 to do the PC+4 addition. We have the next big unit, the register file, the third big unit, the ALU, and the fourth big unit, the data memory. Now these 4 units correspond to the first 4 stages of the pipeline. The first is instruction fetch involving instruction memory. The second is instruction decode, which also involves reading the register file. I have pushed here the branch target computation also to the third stage of the pipeline. This doesn't matter because we anyway need to use a separate adder for computing the branch target, separate from the main ALU. And then the fourth stage of the pipeline is the data memory access, which is not relevant for some instructions. And the fifth stage also involves register file in the write back operation. This diagram does not show all the details because showing all the details will make the diagram very messy. For example, I have not shown here the mux in front of input 1 to the ALU, or the mux in front of input 2 to the ALU, or the mux to select which register has to be written in the fifth stage. One important difference from the multi-cycle implementation is the presence of these large latches. So these are large latches which I have shown here. These latches exist between one stage and the next. And unlike in the case of the multi-cycle implementation, where the latches in the implementation were all used for the same instruction at any given point of time, these latches are going to be used for different instructions at different stages in the pipeline. So these latches here are used for carrying forward information. Whatever information is relevant to a particular instruction execution has to be carried forward in these latches as the instruction moves forward in the pipeline. For example, let us say instruction number K enters the pipeline in cycle number 1. So instruction number K will move to the second stage in cycle number 2, whereas instruction K+1 would have entered the pipeline in stage 1 by cycle 2. The immediate value present in instruction number K has to move from this latch to the next latch as the instruction moves from stage 2 to stage 3. So even though the immediate value may find use only in the third stage, it has to move from this latch to this latch. This movement is something that was not present in the multi-cycle implementation. So the mental picture you must have is the instruction along with whatever is needed for the instruction's execution moves forward from one cycle to another using these latches. Yet another example of this shown in this diagram is the ALU output is computed in the third stage and it is written onto this latch, and it has to move from this latch to the next latch before the write back can happen. That is because this original latch is going to be used by some other instruction in the very next cycle. Since these latches reside between one stage and the next, these latches are named by this convention. So this latch goes by the name of IF/ID to indicate that it is a latch between IF and ID stages. Likewise, this second big latch here goes by the name of ID/EX, and the third latch goes by the name of EX/MEM, and the fourth latch by the name of MEM/WB. We see in this data path that there are two significant places where information flows backward. The first instance is where the branch target potentially has to be written to the PC, and the second instance is where the result of some computation or the result of memory reading has to be written onto the register file. So in this flow of information from left to right, there are two exceptions where information flows from right to left. One is the branch target and the other is the register value being written. And as we will see, these two backward flow of information correspond to the two different kinds of hazards. The first one corresponds to control hazard and the second one corresponds to data hazard. Pipelines don't like these hazards. Pipelines do not like backward flow of information, and these are going to be the problem cases to deal with in our pipeline implementation, specifically the pipeline control. To summarize, we saw that pipeline implementation has to deal with different kinds of hazards, 3 different kinds at a broad level: structural hazard, data hazard, control hazard. Structural hazards are the easiest to deal with. If there is a hardware limitation, there is nothing you can do except stall the pipeline. This will affect the pipeline performance by increasing the CPI from its ideal value of 1. We saw that the pipeline data path involved minor modifications to the multi-cycle data path, and we are going to see that pipeline control is going to be much more complicated, specifically because of having to deal with pipeline hazards.